Welcome back, Gen Chem. How are you? I hope everybody's staying safe and healthy. I want to start a new section within our moles. I'd like to just hit one topic in this video. I'd like to hit empirical formula. So we just had a series of mole videos that went through the mole and did a bunch of calculations, and one of those calculations was our mass percent. So what we're going to do is actually rely on the opposite of our mass percent, or same principle but working backwards. So we're going to ask a chemistry question that's been around for a couple hundred years. What if you have a mysterious substance? How in the world can you figure out what it is? I think most people think of chemistry as figuring out what mysterious substances are. So let's talk about the history of that. How in the world could you figure out a mysterious substance? Somebody hands you a white powder and you want to figure out what it is. Well, wait, that could be illegal. Anyway, legally, if you want to figure out what that is, you would do a couple of different tests on that substance. And if we go all the way back to our history days and we look at J.J. Thomson, back in 1897, when we talked about the history of the electron, that was J.J. Thomson and the cathode ray tube. And we also had some handouts in class, and we mentioned this instrument called a mass spectrometer. And so let's look at a couple instruments, starting with the mass spec and also something called elemental analysis. And I want to give a very, very gross generalization of how those instruments work. Now keep in mind, if you were a chemist in the last 100+ years, this is where you would start. You would use some sort of instrumentation to figure out what kind of mysterious substance you have. So how do these work? Let's just do something super general. You take your little powdered sample, and you would inject it into, let's see if I can draw a syringe. Look at that. All right, you'd inject it into some sort of instrumentation that could take that substance and nail it with a ton of energy. So modern day mass spec or elemental analysis or things like that, you can bombard with electrons, you can zap it with heat. You can do all kinds of things. You can do flame ionization detection. There's all kinds of instrumentation that will help you along this process. Back in the day, they would just nail it with a whole bunch of energy, whatever that energy source is. And what our goal is to break all those bonds. So if you've got any bonds in that substance, you're going to just nail them with energy and break all those bonds. And then you get your substance to travel. And if we think about our mass spec tube that we saw in class, or we think about anything that we could get those things to travel. Remember our glass tubes and our cathode ray tube, our first goal was typically to get those ions or those atoms or those particles or anything we could get our hands on, get those to travel. Well, if you think about it and you break all of your bonds, what are you left with? You're left with whatever the elements are that make up that molecule, whatever it was. If you've broken all of those bonds, let's say you've got something like water. Well, now you've just got hydrogen atoms and you've got oxygen atoms. And we know from our last couple videos that these are different, and they're different in size and they're different in weight. So this is what we're going to take advantage of in all of these instruments. They're different in their weight. So in theory then, your hydrogen is going to be a little bit lighter and faster. Your oxygen is going to be a little bit heavier and slower. So if you can get them to travel somehow, by the time they reach a detector or something that can tell what they are, and those detectors have gotten quite modern nowadays too. There's 5 or 6 different types of detectors on these. In general, what's going to happen is your hydrogen is probably going to hit first. So maybe those hydrogen atoms travel just a little bit faster and they're going to hit that detector first. And then maybe your oxygen atoms are going to hit that detector a little bit slower. Well, if you've got a pretty fancy instrument, this is how you can actually detect which atoms are which atoms. It depends on their speed. How fast could they get from here to here? And then what happens is a little bit of calculus. We don't have the prereq for that, but it comes out to where, okay, let's say your hydrogen atoms are hitting all around the same time, and then your oxygen atoms are hitting that detector around the same time. You can integrate that, and you end up, the end of this whole process, a percent of those atoms. Now, I'm not going to test you at all on this instrumentation. There's way too much variation in how you can break all of those bonds. So there's a whole science behind just injecting that sample. There's a whole science behind those detectors. There's several. It's a really huge area of analytical chemistry. We're not going anywhere near that. But I just wanted you to see that for about the past 150 years, if you had a mysterious substance, where you started typically was to take that substance and get to a percent of your elements. So that's awesome news, because we learned in our last videos that if we take those percents are part of that fixed ratio. So when we saw methylamine, no matter what, we had a percent carbon, hydrogen, and nitrogen. That percent did not change. That's what that fixed ratio meant in that formula. So all we need to do then, if we're getting our elemental analysis, is go backwards. So this time we're literally given the percent of our elements, and we're going to take that and figure out that fixed ratio or that formula. So let's put this into practice. I just wanted to take 5 minutes to give you a gross generalization of the background on why we give a crap. I also included in here some links. So if you are interested in modern day elemental analysis, I believe I gave some handouts on mass spec already, but elemental analysis, if you want to take a look at it and get a little bit deeper, here's some places to start. Again, a lot of that's analytical chemistry. You can get real deep into that when you get into an analytical chemistry class. So for all of these problems, they all have to look the same. What's coming from that instrument is data. You have to be given that data in order to take that and figure out your formula. There is no way to predict those percentages unless you already have the formula. These are connected. You have to have one or the other. You either have the formula or you have the percentages. So let's go backwards. Let's take this data and let's see if we can get to the formula. The first thing I like to do in these, it's a little bit of math involved, so grab your calculator. The first thing I like to do is just double check that we're adding up to 100%. So I'm going to grab my calculator and just do a quick add up. You should add up to 100%. Every once in a while it's just slightly off. If it's slightly off, that's not too bad. This is exactly 100%. Whoa, sorry, I hit the wrong thing. All right, this is exactly 100%. Awesome. So let's make our lives easier. How do we get to that ratio? When we watched those last couple videos, they all had one thing in common. They all went through moles. It's not possible to go from this percent to the formula without having moles in the middle. So, but Dr. Morty, you're nuts. How do I go from a percentage to moles? You can't. We can go from grams to moles. So let's cheat and let's call this 100 grams. All right, just basic math. We know that this relationship is set. This relationship, whatever those percentages are, that relationship is going to lead us. Okay, I don't even know what I'm spelling right now. Maybe I should not be making videos. Relationship. That was awesome. Please don't lose faith in me. Okay, so as we have our percentages, that relationship is set. It's our job then to put that into a formula. So if we have 100%, then out of 100 grams, we keep the same relationship. We're going to have 52 0.14 grams out of that 100 grams. Okay, same thing for our 13 and our 34. So keep the same relationship. That's the important part there. You're keeping the exact same percentage to grams. You're keeping that relationship. Now we can do what we've learned in our last couple videos. Let's take those and let's convert them all to moles, because moles is how we can relate to everything. You cannot go directly to that percentage without going through moles. You will get a weirdo answer. So, all right, let's take carbon. I'm going to go ahead and round, and I'm going to just do 12 for carbon. I'm going to do 1 for hydrogen, and I'm going to do 16 for oxygen. So hit pause for a second, grab your calculator. Let's try and figure out for each one of these what that relationship is in moles. So I'm going to take that first one, divide by 12. We're going to get 4. All right, let's take that second one. Hold on. I don't even need my calculator for that. That's awesome. All right, let's take that last one, 34 divided by 16. I'm getting 2.170625. Good Lord, that's way too many. I'm going to just round that right there. Okay. And that is moles of oxygen. All right, once we're in moles, this is our fixed ratio. So we could literally write the formula right now. We could say carbon 4.345, hydrogen 13.13, oxygen 2.17, done. All right, that is your fixed ratio. Here's the problem. That looks crappy. I mean, when do you ever see not whole numbers there? We don't. So this next step is pure math. This next step is the reason we're going to call this an empirical formula, because what we're going to try and do is get the lowest whole number ratio for our formula. And the best way to do that is to set your smallest one to 1. So how would we set oxygen to 1? We need to divide by 2.17. We need to divide everything by the smallest, and let's see what we get. Okay, so that's going to be 1 for your oxygen. Let's take our 13. And I'm getting 6.05. Okay, 07, and then let's do 4.345 divided by 2.17, and I'm getting 2.0023. All right, now we're getting awful darn close. At this point, it is okay to round. Okay, we are going to round these numbers. This is why it didn't really matter so much that I used the whole numbers over here. We can go ahead and round as long as your values are less than about 0.1. You can totally round. So if I'm looking at this, I'm going to go ahead and round that to 2. And if I'm looking at this 6, I'm going to go ahead and round that to 6, and then keep the 1. So what did we just figure out for our formula? This is awesome. We're going to have CHO. We've got 2 for our carbon, 6 for our hydrogen, and 1 for the oxygen. And we don't have to write the 1. You can leave that off. This deserves a sparkle pen. We just figured out our empirical formula. Now, why is it empirical? Because this is the lowest whole number ratio. Now, we could also have C4H12O2. That would have the exact same relationship. Why we get that lowest ratio is this step right here in our math. So we always start here. Without another piece of information, this is all we can do. You can get to your empirical formula. If you combine this with mass spec, you would get molecular weight. So those two instruments are often used together. If we get our molecular weight, then we can tell if that's really the formula or not. And we'll have another example that we have that in there. All right, so this is awesome. Does anybody know what this actually is the formula for? This is actually the formula for booze. That is ethanol. Why not have a little bit of fun when you're figuring out your formulas? All right, let's turn around and do this process again. If you want to pause for a second and screenshot, I'm going to scroll this down. I also am posting this PDF so that you've got this blank copy so you can try these problems along with me. All right, let's scroll down. Let's do another one. Let's do Carvone. Now this one's getting a little bit sassier. This is going to be a little bit bigger. Let's start that whole process. Let's do the same thing. Oh, sorry. Let's do that same thing. Let's look for 100% on here. Let's see if we've got 100%. Put me on pause for a second. Let's add those numbers up. And let's see what we get. I'm going to do it too. Again, you saw in the last problem, if you're slightly off on these, it is okay to round. In fact, this one, if I add that up, I get a 4 here. So I'm going to go ahead and just keep that as 100%. And then I'm going to transfer all this and call it 100 grams. Okay, so I'm going to go 7.96 grams of carbon. 9.39. I'm going to drop off that 4 grams of hydrogen, and then 10.65 grams of oxygen. So what I'm saying is, if I had a 100-gram sample of Carvone, I would have 79.96 grams of carbon in there, 9.39 grams of hydrogen, and 10.65 grams of oxygen. That's how that works. Remember, this relationship has been set up by that instrument in Mother Nature. Carvone will always have this relationship. That's what makes it Carvone. All right, so let's take each one of them. Grab your calculator. Let's convert them to moles. I'm going to go ahead and round those again. And then let's do the same thing for oxygen. Let's convert all of them to moles. All right, hit pause and grab your calculator. Let's calculate this. I'm going to take that 79.96 divided by 12. Ooh, this is going to get rowdy. Okay. There's 3's there. All right, let's take 9.39. Oh, I don't even need to put that in my calculator, do I? All right, then 10.65 divided by 16. Oh, this one's small. Okay. Look at that. All right, so at this point, we have our relationship. Again, if we wanted to, we could write that fixed ratio. It just would look awful. We could write, this is how many moles of carbon. This is our moles of hydrogen. So we would say 9.39 hydrogen, and then oxygen. Okay, again, just looks terrible. So let's go ahead and do the empirical part. Let's divide by the smallest for each one of these. And let's see what we get. Okay. Holy cow, I got exactly 10 for that first one. Isn't that fun? Okay, 9.39 divided by 0.6663. Whoa, I got 14 for this one, 0.093. And then for that bottom one, I got 1. Okay, now this is less than that 0.1, so it's okay to round that. So I'm going to keep the 14, the 10, and the 1. So what does my formula end up looking like? C10, H14, 1. Awesome. Look at that. That is Carvone. Okay. So really, it's the same process. You start with your percentages. Now, I have to give these. So in a homework problem or a test problem, I would have to give you those percentages. And then you're going to convert to moles. Remember, moles are in the middle of everything we're doing in this section. And then you've got that one math step where you're converting your relationship into a whole number, and you're done. Okay, now how do you make these sassy? There's only two ways really to make them sassy. The first one is the rounding. So what if it's not less than 0.1? And then the second is to include a molecular weight. So let's take and do another example that actually should hopefully have, here's one with a molecular weight, and then we have one right down here that's got a little bit of sassy in the rounding. So there's literally only two ways to make these a little bit spicy. And here, let's do examples of each one. That way you can work your way through everything. So let's do some caffeine. Obviously, I enjoy caffeine. And I'm giving the molecular weight also. So let's start our process and let's see why we even need the molecular weight or why we give a crap. So let's work our way through our process. This looks a little bit rowdier, but let's double check that that's 100%. So grab your calculator. I'm going to do the same thing. I'm just going to add them up right now while we're talking. I'm getting just shy of, but quite easy to round. So let's keep that at 100. I'm getting 99.99, so awful darn close. So I'm going to call that 100, and I'm going to write these all in grams. Okay. All right, let's go through our process. Let's convert them all. I'm going to spread out just a little bit so I have a little bit more room to write. Let's convert them all to moles. Nitrogen, anybody remember what that one is? 14, and then oxygen, 16. All right, grab your calculator. Let's do it. 49.48 divided by 12. I get 4.12. Anybody with me on that? All right, this one I don't even need. Okay, this is moles carbon, moles hydrogen. All right, let's do this one, 28.87. Moles nitrogen, and then let's do oxygen. All right, we're awful close to 1 on oxygen, so let's go ahead and just get that as close to 1 as we can. Let's see how close we get. All right, let's take 4.12. Oh, I got 4. 5. Let me guess. 2, 1. Awesome. We didn't even need to round on those. That looks phenomenal. All right, so let's write our formula then. We've got carbon, hydrogen, nitrogen, and oxygen. So we're going to have 4 carbons, 5 hydrogens, 2 nitrogens, and 1 oxygen. All right, so this is our empirical formula. This is our lowest ratio formula, but how do you know if that's really caffeine? So how you know for sure is you're going to check your molecular weight. Now, how do we compare molecular weights? Grab your calculator and add up the molecular weight for this formula. How much is this going to weigh? We've got 4 carbons, so 4 times 12, 5 hydrogens, 2 times our nitrogen, plus an oxygen. When I add that up, I get 65 grams per mole. Okay, now that is not the same as my molecular weight. So that means the empirical formula is our lowest whole number ratio, but it is not our molecular formula. We have to keep this same relationship, but it is okay if it's doubled or tripled or quadrupled. We just have to figure out how. So I'm going to take my molecular weight, 194, and I'm going to divide it by 65 and see what I get. Okay, let's write that a little bit better. Okay, so 194. I am getting, if I round, I'm getting 3. So what does that tell me? That tells me that I have to triple my empirical formula, or I need to multiply this whole thing times 3. So we're about to get, instead, carbon will have 12, hydrogen will have 15, nitrogen we're going to have 6, oxygen 3. Now you can always double check that. Let's add that up. 12 carbons, so 12 times 12 plus 15 plus 6 times 14 plus 3 times 16 gives us just not at all our molecular weight. Did I just multiply that by 3, right? Okay, if our molecular weight is 194, what did I add up wrong? Let's double check that. Carbon 4, hit pause and see if you can figure it out. Aha, I figured it out. Did you figure it out? This is not 65. This is 97. Now we're in business. So what do we do here? We divide by 97, and then what do you get? 2. Oh, I'm so glad we did this, because we don't multiply by 3, we multiply by 2. All right, so now let's fix these numbers, and what do we get if we are going to multiply by 2? Now we get carbon, hydrogen, nitrogen, oxygen. Let's multiply by 2, 8, 10, 4, 2. If you add that up, you should get 194. Let's double check it. We've got 8 times 12 plus 10 plus 14 times 4 plus 2 times 16, 194. There it is. See how we kept the exact same relationship? We just multiplied by 2. That gives us our molecular weight. So this is indeed caffeine. This is our molecular formula. And see how it compares to the empirical formula? If you don't have the molecular weight, all you can get to is the empirical formula. So if I give you a problem that gives you this data plus the molecular weight, then you should be able to get to the real molecular formula. Okay, let's do one more example. And now this is going to have some sassy rounding. So let's go through our process. I'm going to speed it up just a little bit. I'm going to hope that's 100%. Call that 100 grams. So we're going to have 43.64 grams of phosphorus, 56.36 grams of oxygen. So let's pause for a second and grab your periodic table. What is our molecular weight for phosphorus, or atomic weight? So grab phosphorus is 31. Oxygen is 16. We've already seen that. All right, let's see what we get then when we do that. 43.64. I'm getting 1.4. Let's do the 56. I get 3.5. All right, let's divide them both by 1.4. Let's see what we get. We're going to get 1. And we get exactly 2.5. Oh my gosh, I love it. All right, so son of a motherless goat, we did not get to a whole number. Can we just round this to 3? Oh, Sal, no. No, you can't. This is much greater than 0.1. So we cannot just round it. We've got to do one more math step. Remember, our goal is to get to a whole number. We can't just leave it. We would be right if we said like this. Okay, that is the relationship, but we can't have 2.5 oxygens. So how do we get these to a whole number? We start messing around, multiply by 2 and see what we get, multiply by 3, multiply by 4. In this case, if we multiply them both by 2, we get to whole numbers. So that means our formula is then this. And now we're here with whole numbers. And then you can see that this is not 3. That is actually both are multiplied by 2. All right, so this is actually all the ways that you can get sassy with empirical formula. We've got funky rounding, and we've got molecular